Can you hear me?
Yes, sir.
You are live.
Are we live now? Yeah, okay. So,
Yes.
hello, friends. This is Mr. Sarvesh Varjurkar. We are here for the session organized by Ballarpur Institute of Technology, Ballarpur, under AICT sponsored Prerna scheme for SC/ST students. Today's session is our session number 12, in which we'll see about the various numericals on various algorithm design techniques. This is the algorithm design technique that we have gone through thoroughly in the last video, in which greedy algorithm, dynamic programming, and divide and conquer strategy, we have gone through it in a very proper way. Meanwhile, there are certain amount of numericals that we haven't covered in the last video, and that we are going to try to cover in today's video, in which in greedy we have identified three different algorithms, that is Prim's algorithm, Kruskal's algorithms, and Huffman coding. Whereas in dynamic programming, we have identified traveling salesman problem, salesperson problem, and zero one knapsack problem. And in terms of divide and conquer design technique, we are going with merge sort. So firstly, we'll go with the minimum spanning tree, which is there as a part of Prim's and Kruskal's algorithm. So before that, it is a prerequisite for the concept, which is completely there on the topic, like Kruskal's as well as Prim's algorithm. What is spanning tree? The question arises, what is spanning tree? As the name suggests, it is spanning tree, a tree which contains all the vertices of the graph. A tree which contains all the vertices of the graph. Of course, they are acyclic, called as minimum spanning tree. A spanning tree with minimum sum of weights. On the screen, we are able to see the diagram where one graph is there. From that graph we are able to find out the spanning tree, or I can say like the minimum spanning tree. The reason a minimum spanning tree, it means where the weight that we are going to choose should be minimum, or minimum sum of their weights. Next is spanning forest. If the graph is not connected, then there is a spanning tree for each connected component of the graph. For example, I can also say like the various applications of minimum spanning tree. We are in our day-to-day routine life, we are regularly using all these type of things. Find the least expensive way to connect the set of sites, terminals, computers, etc. I can say like if all the computers, those who are connected in a LAN, should be least expensive, should not should not carry maximum a number of distance in their connections. So to avoid this, it should be the least expensive way. This is again the example. Same thing, I can also give you the example with the help of a town that has a set of houses and a set of roads. If the task is given to you that we have to visit all the houses with minimum number of kilometers, those who are required by connecting with the edges, we are simply called it over here as roads. A road connected to houses U and V has to repair a cost of W U comma V. Goal is to repair enough or add no more roads such that everyone stays connected. There should be every single house should be get connected here or there. But while connecting them, we have to take care that to, to, to reach to any different house, the repair cost or the cost for traveling should be minimum. Everyone stays connected, that is that can reach every house from all other houses, and total repair cost is say minimum. Second is minimum spanning tree, where a connected undirected graph, that is vertices is equal to houses and edges is equal to roads, as I have already mentioned, and the weight u or w u comma v on each edge, that is u comma, which or belongs to the complete edge. Uh, let us find t, which is a subset of e, such that t connects all the vertices, and this is the normal thing. There are certain properties of minimum spanning tree where minimum spanning tree is not unique. If you are connected, if you are given the three nodes like this, and you are able to solve, sorry, you have to ask to draw the uh, minimum spanning tree or possible minimum spanning tree, you can able to draw, like you can select this particular weight, sorry, this particular age and this particular age. This may be the tree, all the nodes are connected, one is having the weight 2 and another is having the weight 1. The complete cost of this unit of this tree is, or minimum spanning tree is, 3. Same thing, if you can also choose the different path like this should be connected with this node by weight 2, and this is again connected with this node by weight 1. Ultimately both can be applicable, both can be usable, both can be the minimum spanning tree. Yes, they always remember that while drawing the minimum spanning tree, it should not carry any different cycles with them. Why? We cannot take out any edge of the cycle and still have all the vertices connected while reducing the cost. One important note I have mentioned is the hash of edges in the MST is equal to number of edges in the minimum spanning tree is equal to vertices minus 1. Always be remember this thing. The number of edges in the number of edges in the minimum spanning tree is always equal to the total number of vertices minus 1. That's it. If n are there, you can say like n minus 1. If 10 edges are there, sorry, if 10 vertices are there, the number of edges should be 10 minus 1 is equal to 9. Growing a MST. How to grow the MST? That is minimum spanning tree. In a generic approach, I can say like grow the set of A edges initially are empty and incrementally add all the edges to A such that they would belong to the MST. Add only safe edges, those who looks safe, those who can able to select to connect with each other with of course minimum number of weight. In that case, from A, if I am selecting A to B, there is weight 4, so I am going to select that one. B, there are two different way, one is going to H, another one is going to C. I am going to select that C. Why? It is having the less weight. After C, there are three different edges and both are minimum. Sorry, all the three are minimum. C to D, there is 7. And if we don't get 7, there is no any path to reach to D. One is having 14, another is having 9, and another is having 7. So we are going to choose 7. Why? Because it is the lowest possible way to connect from the node C to the node D. And H, which is safe if and only if all the subset of some MST. That's it, like this. And then we'll able to know that while A is not a spanning tree, do find the edges u comma v that is safe for A, and which are equal to A, which is a subset of u comma v, and then return A as well. How do we find the safe edges? The question arises later on. We'll say that is it safe for A initially? You can able to select any different node whatever you want. At the end of the time, at the end of the problem, we are definitely able to find out all the possible nodes with minimum number of weights with them, that can connect with minimum number of weights. Why not we choose the edge with minimum weight h comma g? The reason the reason is very simple. We haven't choose h comma g as if we are it is the last node, but we can choose definitely h comma g as if our first priority, definitely as if our first priority. It depends up to you. It is a partition of vertices into disjoint set s and v minus s, v to s, I can say. And h crosses the cut, say s comma v to s, if one endpoint is in s and another endpoint is in v to s. It can be possible to find any different node. It can be possible to find any different node which is there, which gives you minimum weight and which gives you minimum weight to reach from one node to the another node by having any different kind of vertices, sorry, by having any different kind of edges like this. So this is all about the MST. Now we'll go with the Prince algorithm. Again with the same example. See what Prim's algorithm says that the edges in the set A always form a single tree. The edges in the set A always form a single tree. I repeat, single tree is very important. Uh, just hold. Huh. Where it can start from any arbitrary node. Arbitrary means you can start it from anywhere in the loop, anywhere in the graph. You can choose here. I have choose A as a part as an arbitrary node, but you can choose any different node whichever you want. Find a lightweight, sorry, find a light edge crossing, add the edge to A, and then go on. Prim's algorithm is to find the minimum cost spanning tree that uses the greedy approach. As we all know, that Prim's algorithm shares a similarity with the shortest path first algorithm, where Prim's algorithm is in contrast with Kruskal's algorithm that can treat the node as a single tree and keeps on adding new nodes to the spanning tree from the given graph. To contrast with the algorithm, with the Kruskal's algorithm, and to understand the Prim's algorithm better, we are going to have with this example like this. Firstly, I have, that's why I have mentioned it in the dark circle. I'm going to choose A as my arbitrary node. From A to B, sorry, from A there are two different paths. One is going to B, another one is going to H. In that case, I'm going to choose the smallest one from A to B, that is 4. From A to B, that is 4. Yes, this one. Next, in terms of use a priority queue, it can contain vertices which are not yet included in the tree, that is V minus VA, and all that edges, sorry, all that vertices we are going to write it in that queue part. We associate a queue key with each vertex V, and minimum weight of any edge U comma V connecting V to VA that can be able to design over there. Accordingly, we can also adding after adding a new node to VA, we can update all the weights of the node, and that is adjacent to it, whatever the weight that we are whatever the age that we are selecting it, and accordingly you may able to find out like this. A to B, I have chosen 4. Then H is having 8, so I am rejecting it. Next, all the rest are can be able to drawn over here. I can able to drawn like this, and then if the things are going to change from B, of course, Prim's algorithm stays that it should be in a complete connected mode. So from B we have two different paths. One is H, another one is C. I have chosen B to C because it is having less weight. Now when my cursor is at C, there are various different paths. C to I is 2, C to K is, sorry, C to D is 7, C to F is 4. In that case, I have chosen C to I first. Then my cursor is at I. From I, two nodes I am going to visit, that is possible to visit. One is H and another one is G. So I am going to choose which one is minimum from that previous node, that is C. So C can be connected with F. Again, C can be connected with F, of course, and after that reaching to F is connected to G itself. G is connected to two different nodes. One is I, which is already been visited, so no need to go there. One is H, so I'm going to go with H itself. So when reaching to H, the weight should be like this. And now the only unvisited nodes are D and E. So D and E, they are having the weight 7 from C, and uh, one age like E is remaining. So I can choose E from D itself. That can gives you the things in like this. It's a complete structure of your MST where A to B B to C, C to I, C to F, F to G, G to H, C to D again, and D to E again. So this will be your last last spanning tree, which is a minimum spanning tree. Rest of the other rest of the other tracks are there as a spanning tree. You can able to find out n number of spanning trees from the given diagram, but the answer or the exact minimum spanning tree is exactly like this. Now you can add the number of, you can count the number of edges that we have selected. A to B 1 edge, B to C 2 edge, C to D is 1 edge, that is 3, C to I 4, I C to F 5, F to G 6, G to H 7, and D to E is 8. There are, if you count it properly, there are 9 different vertices with you. Ultimately our spanning tree is having 8 different edges. Whatever the summation of all of this, that will be your value for minimum cost spanning tree. The addition of all these tracks will be nothing but your uh, uh, the value required for that MST. Hope you understand. This is the normal syntax algorithm for that prims. Fibonacci can definitely help the algorithm, and I have already mentioned all these type of things. Prim's algorithm is a great
Due to some technical issues, servicer is not into the network. He will be right back in a short time. You guys are all requested to wait. I'm very sorry for inconvenience. Thank you.
Sir, voice is clear, sir?
Yes, sir, you are connected.
Okay,
Add your screen.
okay. I'm sharing the screen again. Okay,
Screen is, sir, added. Sir, live.
okay, sir. Sir, I think we are able to see the screen now.
Pardon?
Yeah. Where we can compute the average depth of the leaf as well, in which the various nodes which are already given to you, like A, B, C, D, and E. You can able to calculate the actual position of each and every nodes, and along with that, with the help of with the by referring it from the given nodes, sorry, given codes, you are able to find out the location of each and every uh, nodes in the given tree. This is all about the Huffman algorithm or Huffman coding, where you can derive it from the two rarest atom that will be that will have the longest code word, or code word for rarest atom may differ only with the last bit itself. Can also be possible in this Huffman coding. There are mainly two different parts. First one to create the Huffman tree. Another one is to traverse the tree in the different way. But while traversing the node, you have to take care of the input should be the number of node in the Huffman tree, and the code assigned to the and code assigned from the the previous call, that means the previous nodes itself. So you need to take care of all these type of things, and you are able to find out you are able to find out the code for any different node in the given tree of any different length. I repeat, that length will be any different number or any different level for the given nodes. If the weights are like 5 4 6 5 4 5 6 7 11 20 14 and 21, you can able to draw the Huffman tree for the following data set or data values that can show the internal weight. Firstly, you have to arrange all the elements in the ascending order. it is already been in the ascending order, and then by combining, by merging them together to find to draw the tree, and on after merging you are going to find out the whatever the complete addition or whatever the summation is, like that the top is built with the root of that tree. And from that root you have to put, you have to mention the left side there should be 0, and on the right side there should be the code always been 1. Always start it from the left node, and from the root node you have to find out the uh, code for a particular node. The most amazing induction proof is like induction on the number of code words, that is the Huffman code finds an optimal code for n is equal to 1. Suppose that Huffman algorithms or Huffman coding algorithms find an optimal code for the code size n. Now we can able to consider, we can consider a code of size n plus 1 itself. Next is we can also modify the following with respect to the WPL, uh, along with the length, and 29 is the actual total. You can see the given input is like 6 4 5 and 6, I can say 3 6. So you have to arrange all the nodes in ascending order. All the leaf nodes are nothing but the given input. You have to arrange all the nodes in ascending order first, and with that ascending order you can able to find out the best possible tree for the, for that given numerical, or for that given algorithm named it as Huffman coding. Finish the induction proof, we can able to finish it out by applying the tree constructed by Hammond, which is Huffman, which is shown by T. X is nothing but any different code, and you can able to read it out all these things. uh, Next important problem, now we'll go with the traveling salesman problem, the dynamic programming approach. We are going to cover the traveling salesman problem as well as one more algorithm on that dynamic programming, and lastly we'll go with the merge sort. Traveling salesman problem, how it works. Know that traveling salesman need to travel all the cities or all the nodes given to them. The number of weights has been should be very less, should be optimum, should be minimum. It is a part of minimum cost spanning tree as well. It is the example of minimum cost spanning tree as well, where the optimization problem is we need to find the least cost tour starting at A, traveling through the other three cities exactly once, and returning to the city which from which he has started his journey. If he starts from A, he need to end at A itself. He need to end at A itself. Next, decision problem is there a traveling salesman problem tour with the cost less than K. These are the two scientists. They have discovered the questionnaire, Sir William Hamilton and T.P. Kirkman. So it is an Icosian game. It is developed in the year 1875. Sorry, 1857. And these are the scientists. They have the path to. They need to find it out for the car, and like this, they have to visit all the path from the given there over there. It has been invented in the year 20th century, and 1931 to 32. As started by Merrill Flood, and these are the history of this and various applications for that traveling salesman problem. There are various n number of applications, I can say, like school bus routing. You can able to apply in robotic welding in the car industry. You can also able to apply it in printed circuit board drilling, as well as cutting the integrated circuits as well, job processing, chemical plants, everywhere you can able to use like this. These dots are nothing but the nodes, and the connection between the two nodes are nothing but the edges. The problem statement is like is a very clear. A travel needs to visit all the cities from a list where distances between all the cities are known, and each city should be visited just once. What is the shortest possible route that he visits each city exactly once and returns to the original origin city? That origin city is nothing but the city from which he started. The solution is traveling salesman problem is the most nurturous computational problem which can use the brute force approach to evaluate every possible tour and select the best one for n number of vertices in the graph. If the vertices in the given graph are n, then there are n minus 1 factorial number of possibilities. N minus 1 factorial number of possibilities. Instead of brute force using, we are using dynamic programming approach to the solution that can be obtained in lesser time. So there is no polynomial time algorithm is there. Uh, that's it. And then in terms of analysis, I can say like in the following example, we are illustrate that the steps to solve the number of to solve the traveling salesman problem. We can able to complete or it can be applicable in complete or incomplete graphs, symmetric versus asymmetric cost matrix, upper triangular cost matrix or triangle inequality holds, as well as circulant cost matrix and bipartite matrix as well. We can able to see take it in the normal example or normal four nodes tree, a four nodes graph where find it can find the least cost to starting at A and traveling through the other three cities exactly once and returning to A. So from A to A, it requires 0 weight. A to B, it requires 3. A to C, one arrow is there, one weight is there, it is having 4, and A to D, it is 6. B to A, there is one arrow, it is having 2 weight, and B to C is 5. B to B is of course 0, and B to D is 2. Accordingly, all the weights are there. These are the generating permutations to go from all the cities to the another cities and return to the original city itself. So by applying this naive, we have all the twos and their cost. If we are started from A to B, B to C, C to D, D to A, it requires 18. A, B, C, D, C, A, it 19. A, C, B, D, A, it is 15. A, C, D, B, A, it is 15. A, D, B, C, A, it is 24. A, D, C, B, A is 19. Whatever the minimum one, whatever the minimum path, we need to select it out, and the minimum we are going to find it out in one complete tow is like ACBDA is 15 or ACDBA is again 15. So we can choose any of them for our minimum cost to travel the whole all the cities in the given graph by the salesman. This is the timing for naive algorithm, and that estimates 17 cities. It requires averagely 34.9 days, nothing but 2.09 multiplied by 10 to the power 13 twos and so on. I have already mentioned the number of possibilities of spanning trees. To find the spanning trees is like if there are n edges, n minus 1 factorial, n minus 1 complete factorial number of steps can be possible, or possible twos are like this. Uh, these are the weights along with the tracks given with them. A, B, C, D, A is 22, A, C, B, D, A is 22, and so on like this for that given constant traveling salesman problem. And if the constant is there, the only cost matrix that have the same cost for all the traveling salesman twos are those with entries that satisfy Cij is equal to Ai plus Bj. And you can able to draw the proof as well, where the linear problem is like this, and the traveling salesman problem can also be solved by using this particular track. It can also be solved by applying the minimum cost spanning tree, or I can say that minimum spanning tree itself. We can pick next smallest stage that can connect it to the partial tree, but not forming a cycle. There should not, it should not form any cycle, as if these are the properties of minimum cost spanning tree. So in that minimum cost spanning tree, it may not allow the cycle for any different nodes while visiting it from the from the edges itself. To form a traveling salesman problem tour, we can trace the minimum spanning tree twice, thrice, using shortcuts if possible. You can able to find it out. It gives A, E, B, C, D, A. and the cost of this tour is 31. You can if you are going to add all the weights, and the spanning tree has cost 19 itself, which is very much less than the traveling salesman problem. Approximation can also be applicable, and search tree can also be possible to find it out, where the branch and bound techniques possibly reduce the number of nodes those who are not visited. And it can also be find the while the possible list is not empty, we can also apply, or we can able to do select the node for smallest estimated cost and remove it from the list. We can generate the children of selected node and add it to the list. If children completes a tour, we can update the optimal tour. Otherwise, estimate cost of the completed tour using this child can also be possible. If estimated cost is greater than the current optimal, we have to remove the node from the list itself. So this is the first example from which it requires the elapsed time is 1.05 second and total nodes visited are 7 lakh 10,050. So this is the number from the given diagram. Ant colony optimization is again the part of that the dynamic programming, which ant can find the shortest path to the food, the deposit phenom on trail, and the trails with most phenom can get most ants, and it can basic searching behavior with the random character itself. So again the same that it can follows the travel, or also applicable it for the traveling salesman problem, where we need to find out the track from the source to the destination itself and again return back to the source again. Now when we are going to deal with the next different part, as if we have to go with the next different part, that is after dynamic programming will the next different dynamic programming is the example of 01 knapsack problem, where we are going to cover it in today's video. In which 01 knapsack problem, it is a set of s of n atoms, with each atom is having the weight, which is a positive weight, and the benefit or the profit, which should again be the positive profit. Yes. The goal or the target for that knapsack problem is choose the elements or atoms with maximum total benefit but with the weight at most w. The weight should not exceed more than w. So 01 knapsack problem can also be solved. If we are not allowed to take any fractional amounts, then this is the 01 knapsack problem. In this case, the objective is to maximize the benefit, or I can say the profit as well. Uh, in 01 knapsack, atoms cannot be broken, which means the thief should have to take the atom as a whole, or it should leave it. It may be 0, 0 means leave it, or it may be 1, that means it can be take it. And the constant is like I to t limit wi, which is not exceed than capital W. Even when the set of things are like this, where the weight are 4, 2, 2, 6, and 2, and the benefits are 20 for the given 5 items, 1, 2, 3, 4, 5, $20, $3, $6, $25, and $80. The box of width 9 inch, or sorry, 9 total should be the limit should be of 9. It means he cannot add more than 9, no, more elements which are greater than 9 weight he cannot add. So definitely he can add the weights of the item which should be less than or equal to 9, and which can give him the maximum profit itself. So he can add element number 5, atom number 3, atom number 1, since it carries the weight 9 itself. Choose the atom with maximum total benefit but with the weight at most W. It can able to apply the problem that is the first seems to require at a lot of time, It may be, I can say, like it may be exponential as well. It can provide that can be provided to us with some simple sub problems. Like the sub problems can be defined in terms of a few variables such as j, k, l, m, and so on, and any different list. On sub problem can be of optimality. The global optimum value can be defined in terms of optimal sub problems as well. The 0 1 knapsack cannot be solved by greedy approach, and the greedy approach does not ensure any optimal solution, since we know that the greedies find the locally to globally one. And instead of selecting the items based on the overall benefit, we need to select the items on selected benefit ratio, where the pi upon wi or benefit I bi upon wi. Consider the following set in terms of knapsack. We can able to select whatever the elements which are there, which are giving us the maximum profit with the stipulated amount of weight. The stipulated amount of weight has already been there. We are unable to exceed the limit of that box, and within that limit we have to manage such different items that should give you the maximum benefit, or that should give you the maximum profit itself. 0 1 knapsack algorithm can be there in terms of it can recall all the definitions of that, and a polynomial time algorithm, since w may not, it's not a polynomial time algorithm where the w, that is the weight, may not be the large, and this is a pseudo polynomial time algorithm as well. So this is all about the knapsack problem, where the weight of your box, in which the number of quantity which are applicable is there, and from that you should you are able to use that only values or that only elements to your sack. It may be which will give you the maximum amount of profit, or maximum amount of weight, sorry, maximum amount of benefit within the stipulated amount of weight itself. Merge sort, it is the part of divide and conquer method. The last topic of today's session is merge sort. One example I'm having: merge sort is a recursive sorting procedure that uses order of n log n comparisons. To sort an array of n elements, we perform the following steps in a sequence. If n is less than 2, then the array is already sorted. Firstly, we need to sort all these elements into two different parts, as if we have to divide it into two different parts. Sort the left half first and then the right half of the array using merge sort again. How that merge sort works, with the help of one example, I'm going to explain it right now. Yes. Otherwise, if n is less than 2, then the array is already sorted. If n is less than 1, then we can perform the following three steps. First is sort the left half of the array using merge sort. Sort the right half of the array using merge sort. And step number three is merge the sorted left and right halves itself. How? Merge sort is a technique that is used on based on divide and conquer technique. We know that with the worst case time complexity is n log n, and it is one of the most respected algorithms in sorting. Merge sort divides the array into two equal halves and then combine them to the sorted manner. To understand, we can now sort the, see, if we have given the list like this: 12, 16, 17, 20, 21, and 27. Two lists on the left we have given 12, 16, 17, 20, 21, 27, and on the right 9, 10, 11, 12, and 19. Compare 12 and 9, we'll get to know 12 is greater than 9, and 9 is the new one which comes first, since we are sorting it in ascending order. So we are now going to deal with 9 itself. 9 will be the next, I mean 9 will, we are going to point it out of that stack of that given input. And then we are now comparing 12 with 10. Again 12 is less than, sorry, 12 is greater than 10, so we'll put 10 first after the 9. Then we need to compare 12 and 11, the next element. 11 is less than 12, so it should place in the beside the 10, because we are arranging it in ascending order. So 9, 10 and 11, and then 12 with 12. So 12 we are going to place it after 9, sorry, after 11. So 9, 10, 11 and 12 will be your new sorted order. Then compare 16 with 12. So 12 is less than 16, so we'll keep 12 first. The next element is 19. Compare 19 with 16. 16 is less than 19, so we'll keep 19 over there, sorry, 16 over there. Compare 17 with 19. 17 will keep after that. Compare 20 with 19. So 19 is less than 20, so we are applying 19. We are finding the sequential order. Now look at the sequential order. It is sorted or sorted sequential order. It is like 9, 10, 11, 12, 12, 16, 17 and 19 again. Check out 20 and empty the list. You can simply check out the 20, and you may now apply 20, 21 and 27. In terms of that, we can divide it into two different parts, divide into four different parts, again 2 2 2 2, and then simply single. Firstly, the list of elements, it you can see like the complete list of elements they are having. Original one, uh 4 5 6 7 8 different elements, and we have divided it into two different parts of 4 4 each. 24, 13, 26 and 1 is the first half. 12, 27, 38, 15 is the second half. And then again this particular divide into 4, that means of this 4 we, sorry, of this 4 we need to again divide it into two parts. On the left hand side 24, 13, 26, 21, and on the right hand side 12, 27 and 38, 15. 8, if we are going to divide it into 8, so unless and until all the elements get divided, no further divisions are possible, so we need to divide it till that extent. Now then compare, or now then merge it together. 24 is compared with 13. 13 can be compared with 24, and 13 is less than 24, so we'll keep 13 first and then 24. In terms of 1 with 26, 1 is less than 26, so we'll keep 1 first and then 26. Same thing we have to apply it everywhere. And after that we are now getting the sorted list of two elements itself. Now we are going to combine it them to get the one complete list of elements. So 1, 13, 24 and 26 is the sorted order for that particular first half, and 12, 15, 27 and 38 is the sorted order for the right side part. By combining or by merging them together, we'll get the complete sorted list in terms of 1, 12, 13, 15, 24, 26, 27, 38, like this. How merge sort work? This is the best example. Just now I have initiated and I have explained it in that particular way, where an execution of merge sort is depicted as a binary tree. In terms of binary tree, I can able to divide it into two different parts and so on to get the complete merge final order, or the complete sorted list in the ascending order itself. I can definitely find it out by applying this merge sort. If there are no any changes, the sequence of the appearance of atoms in the original, now we divide the arrays into two different halves, and then divided into two different halves can again be get divided into two small parts, and unless and until no further divisions are possible. Recursive call merge and merge again and again, we can get the complete sorted order. The complexity of merge sort is like number of passes. For one, if the one number of pass is there, 2 to the power k minus 1 or n by 2, and the merge list length is 1 or n by 2 to the power k, which is less than or equal to 1. This is all about the multiplying the number of merges by maximum number of comparisons per merge. We get this type of things. 2 to the power k minus 1, 2 to the power 1 is equal to 2 to the power k, but k is equal to log n, and hence we get log n dot n comparisons, or order of n log n comparisons, as a average case time complexity for merge sort. This is all about the today's video. Over to you, Neeraj sir. Neeraj sir. Yes, Neeraj sir.
Okay, sir. Sir, am I audible?